top of the hill, goes careening down to the bottom, goes around this loop, and then eventually will stop. So the first question, it says indicate on the figure the point P at which the maximum speed of the car is attained. The idea here is that in physics you can always trade height for speed. In the language of physics, we would say that you can turn potential energy, which is going to be maximum up here at point A because it is the highest point, for kinetic energy. As the cart rolls down the hill, it rolls faster and faster and faster until finally right down here at the bottom, that's going to be point P where the cart is moving the fastest. At any point higher than this point P, the cart has to be moving a little bit slower because some of its kinetic energy has changed into potential energy. The second part of the question says calculate the maximum value of this speed. I'm not going to show you the calculation, but I'll tell you what it depends on. The speed at any point, whether it's down here at the maximum velocity or at any other point along this track, is going to depend on two things. The first is the acceleration of gravity. We're going to assume that we're on the Earth, so that's going to be about 10 meters per second per second. The second thing it depends on is height. And this is going to be change in height from your initial position, right? And so if we're going from point A at the top to point P down at the very bottom, that's a difference of 90 meters, yeah? But you could pick any other point on here. For example, if point A is 90 meters above the ground and point B is 50 meters above the ground, the difference between them is 90 take away 50, 40 meters. And so we could calculate the speed at point B by using the gravity on Earth and the difference of 40 meters in height. Yeah. And so that's how this plays out. Basically, it amounts to the further you fall, the faster you go. Calculate the speed of the car at point B. Well, I just explained how you would do that. You would take the difference in height between points A and B, and then you would include the gravity of Earth. And there's a few more details than that, but that's the basic idea, right? On the figure of the car below, so the car is upside down, meaning that it's at point B, it's going around the loop. What are the forces acting on it? Well, there are two. Yeah, there's the weight of the vehicle trying to pull it down towards the center of the Earth. There's also the normal force of the track pushing down on the car. And both of those combine to make the centripetal force that keeps the car going around the circle. Calculate the magnitude of the forces identified. The normal force is going to depend on, well, I don't know exactly how to put this into words, but if you go to the last section of your Chapter 5 notes, you'll find that the normal force depends on weight and centripetal force. Yeah? The weight is just mg, depends on the mass of the cart and the gravity of the Earth. This is an interesting question in Part D. Suppose that friction is not negligible. How could the loop be modified to maintain the same speed at the top of the loop? Well, the idea is that if friction isn't negligible, as soon as this cart starts going down the hill, it's plowing through atmosphere. It's losing some of its energy to all of the air, right? It's literally heating up the air as it goes down this track. Not very much, but a little bit. There's also friction between the cart wheels and the track, so it's heating up, the cart, I should say, is heating up the track a little bit. And all of that contributes to losing energy. In other words, all of the potential energy at point A is not being converted into kinetic energy down here at point P. Some of it's being lost to heat. And so when the cart gets to point B, it's not going as fast as it ought to go because it's lost energy to heat. And so what you would have to do is lower this track a little bit. You have to lower the track because the cart doesn't have all the kinetic energy it would if we didn't consider friction. Yeah. And so as it comes around, it has less kinetic energy. So if we lower point B a little bit, that means it'll go around the loop and it won't have to go as high, and it will have enough kinetic energy to get around the loop.